All right, so today we are covering the last section of Chapter 11. We're looking at analysis of variance. Now, this could either be a very short section or a very long section, depending on how much detail I want to give you. So what I'm going to do is I'm going to go ahead and go through an example. I have to go through some definitions, of course, and there's a lot of explanation as far as why we do what we do. So I will make sure at the end to tell you exactly what you need to focus on so that you know what to expect. Okay. So analysis of variance, also known as ANOVA, abbreviated as ANOVA, which is A-N-O-V-A. And let me go ahead and write that out so you know. So analysis of variance is known as ANOVA. So analysis, this is the analysis of variance. All right, so we're going to be looking at one-way analysis of variance. So it's a one-way ANOVA. We're looking at one-way analysis of variance, which is used for testing hypotheses that 3 or more population means are all equal. All right, so we're testing if population means are all equal. Now, it's only for 3 or more. Remember back in Chapter 9, or actually it was in Chapter, no, yeah, it was Chapter 9. Back in Chapter 9, we already had a test for when we're comparing two means. Well, here we are comparing more than that. So analysis of variance is used to test whether or not 3 or more population means are all equal. Okay, so we compared 2 population means back in Chapter 9. So now we're comparing 3 or more population means. All right, so the distribution we're looking at is something called the F distribution. Now, what does this look similar to? When you look at this distribution, what does that look similar to? Right, it looks very similar to the chi-square distribution, right? Yes. Well, it happens that the F distribution is actually a ratio of 2 variances. Okay, so the F distribution is a ratio of 2 variances. And so the shape of it looks very close to the chi-square distribution. You're right. All right, well, what are the similarities here? We have it's starting at 0 and it's skewed to the right. Okay, so we are still treating p-values as we have always treated them. If you have a small p-value, and usually the way that we determine if it's a small p-value is we say if your p-value is less than alpha, so small p-values lead us to reject the null hypothesis, and that's what we've always been doing. So when your p-value is less than alpha, you're going to reject the null hypothesis. When your p-value is less than alpha, you're going to reject the null hypothesis. Again, it's what we've always been saying. So it holds true again. In this case, our null hypothesis is a statement about equality. So the null hypothesis has the statement that all your means are equal. So when you reject the null hypothesis, you're rejecting that all means are equal. Large p-values, so if your p-value is larger than alpha, then you fail to reject. So that was p-value greater than alpha, you fail to reject. Again, that's what we've been saying all along. Now, let me just correct something on the first part. I said that you're going to reject the null hypothesis if it's less than alpha. That's less than or equal to alpha. So we're going to be paying attention to p-values. Either the p-value is less than or equal to alpha, or it's greater than alpha. And if it's less than or equal to alpha, then we reject the null hypothesis, which means that we reject that all means are equal. Okay, so this part is very important. So I've already stated that analysis of variance, we're going to be testing the equality of 3 or more means, 3 or more population means. Okay, so we're testing to see if 3 or more population means are equal. But we do this by analyzing sample variances. So we are determining whether 3 or more means are equal by analyzing what's happening with the sample variances. And that's where the name comes from. It's ANOVA, analysis of variance, right? It's analysis of variance. It's used to test the claim that 3 or more means are equal, but yet we're analyzing the sample variances to do that. So let me write that out. So again, this is a test for determining whether your population means are equal. Again, it has to be 3 or more population means. So you have to be looking at 3 or more sets of data. And just by looking at 3 or more sets of data, you can see whether their population means, you could determine whether their population means are equal or not. And we do this, we come to this conclusion by analyzing sample variances. So analyzing a variance is very important in determining what's happening with the population mean. Okay, let me get my pointer. So a one-way analysis of variance, which is what we're doing. This is going to be used with data categorized with one treatment, which is then a factor. And this is just a characteristic that allows us to distinguish the different populations from one another. All right, so I'm going to give you an example of that. I think we're talking about cars today. I'm giving you data, and it has small cars, medium cars, large cars. So there the treatment would be the size of the car. And that's what characterizes one from the other. And we do have requirements. Now, the populations have to be approximately normal. They have to be approximately normal distributions. And we have to assume that the populations have the same variance or same standard deviation. So that means that you're pulling from the same group. So you're taking your population and you're dividing it into separate groups. So the populations are going to have the same variance. So somehow you know that they all have the same variance or standard deviation. We have to have simple random samples. They have to be independent of each other. That's very important. They have to be independent of each other. The different samples are from populations that are characterized in only one way. So they can only be distinguished by one factor. Okay, so this is the part that you really need to pay attention to. How do you come up with the p-value? How would we obtain the p-value? We are going to use our calculator, or StatCrunch also does this. We're going to use our calculator to come up with our p-value, which will tell us whether we reject or fail to reject the null hypothesis. Okay, so being able to know what to do by simply looking at the p-value is what's important. You need to be able to do that. Okay, so in our calculator, let me show you where that would be. I don't have any data right now to put in there. So what I'm doing here is I'm just showing you where ANOVA is. So right now you should see the calculator on your screen. And what you're going to do is you're going to go to Stat. Let me clear that one more time. I wasn't in the right window. Okay, so you're going to go to Stat. Then you are going to right arrow over to Tests. And there you should see ANOVA. Now it's probably at the very bottom. So instead of scrolling down, 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 you can just scroll up once and you should see it. It's the very last one. So you select ANOVA. Now you're going to have 3 or more data sets. These are 3 or more samples that you're looking at. So they're going to be somewhere, they're going to be in your lists. Now remember, I started off saying I didn't have any data here. But when you do enter your data, you're just going to tell it where it's at. So notice how I'm entering my lists and saying where my data is. So what this is going to do is it's going to give me my p-value, and then the p-value is going to help me determine whether I reject the null hypothesis or fail to reject the null hypothesis. The null hypothesis is the statement that all of the means are equal. All right, so this is assuming I just have 3 lists. Now remember I said I don't even know what data is in there. Later we'll enter our data. And of course it said there is an error because I don't have data in there. But that's where you're going to find ANOVA, under Stat. Okay? All right, so we're going to come back to that once we have data. All right, so what I'm going to write here is that on the calculator, you find this by going to Stat, and then you're going to select Tests, and then you're going to look for ANOVA. And you're going to enter all of the lists wherever your data is. I'm just putting ... there because I don't know how many lists you'll have. You'll at least need to have 3. So the minimum is 3. You have to have 3 sets of data because we're comparing 3 means or more. So the very minimum is 3. All right, so that is where you will eventually go to get your p-value, to determine whether we reject or fail to reject the null hypothesis. Okay, and what I said was that if your p-value is less than or equal to alpha, that's when we reject the null hypothesis, which has the statement that all means are equal. All right, so if you reject the null hypothesis, if we reject the null hypothesis, that means that at least one of those means is different. They're not all equal. All right, so what I want to do is I want to show you something kind of shows that graphically to you, what I just said. All right, so if you reject the null hypothesis, that means that at least one of the means is different. Okay, so that is this statement right here. So the null hypothesis has this statement where all the means are equal. The alternate hypothesis says that not all the means are equal. So if you reject the null hypothesis, that means the null hypothesis is not true. And that means that one of the means is different, or maybe all of the means are different. All right, so in this case, only one of the means is different, so we would reject the null, right? If that's happening, we reject the null hypothesis. This one over here is saying that all of the means are different. Again, we reject the null hypothesis. The only time you wouldn't reject the null hypothesis is if all the means are equal. Okay, so a p-value that's less than or equal to alpha will reject the null hypothesis. And so therefore, we would say that the null hypothesis is not true. And if the null hypothesis is not true, then you're looking at either one of these situations, where all of the means are different, or at least one of them is different. Now, we don't know which is the situation here. All this is saying is that at least one of the means is going to be different. But I wouldn't be able to tell you which. We're not saying which one is different. We're just saying that one of them is different. All right, so that's what that says. And then down here, it's the opposite. If the p-value is greater than alpha, then we're going to fail to reject the null hypothesis. So if I fail to reject the null hypothesis, that means I still believe the null hypothesis. If I fail to reject the null hypothesis, then all of the means are equal. And if all of the means are equal, then this is the situation that I have. So notice that all of the means are the same. So if you fail to reject the null hypothesis, then the null hypothesis is true. And what the null hypothesis says is that all means are equal. And that's what we see happening here. So all of the means are equal. All right, so the setup for the null hypothesis and the alternate hypothesis, that never changes. That's going to be the same for all of our problems. Okay, so word of caution here. When we conclude that there is sufficient evidence to reject that all population means are equal, when we conclude that there is sufficient evidence to reject that all population means are equal, we can't conclude which mean is different. That's what I had said before. So when we reject the null hypothesis, which tells you that the population means are equal, when we reject that, we're not concluding which of the means is different from the others. That's not what ANOVA is doing. There are other tests that test for that, but not what we're doing. All right, so we're just testing whether they're equal or not. We're not saying which ones are not equal. Okay, so before getting into more detail, before getting into more definitions, I want to just go ahead and do an example, and then we can kind of go through the specifics later after this example. So what is it that you're going to be doing in this section? You're going to be given data, just like I have here, and we're testing the claim. You're going to be asked to test the claim. In this case, it says test the claim that the samples come from populations with equal means. All right, so population with means that are all equal. That's what we're testing. So if you have more If you have 3 or more means, then we're using ANOVA. If you only had 2 means that you were comparing, then you're back in chapter 9 because that's where we're comparing 2 means. But now we have 3 or more. So in this case, we actually have 3. So this would be perfect for ANOVA. All right, so I am going to, let's go ahead and enter this on let's use our calculator. Now we have data, so we can enter this. So you are going to put this into L1, L2, and L3. So you have small cars, medium cars, and large cars. So our factor here is what makes this different is the size of the car. These are measurements. This is the chest deceleration measurements from car crash tests. And we're trying to see if there is a difference in the mean chest deceleration in car. So as being in a small car versus being in a large car, what is the distance that your chest travels when there's an impact, when there's a car crash? So small cars, do you have greater chest deceleration or more? So we're trying to see if there's a difference in the means from the 3 cars. So either we're going to say that no, they all have the same mean. That's the conclusion we're making about our population based on the sample. Either we're going to say they all have the same mean, or no, at least one of the means is different. But I'm not saying which one is different. Although you can kind of see what's happening with our sample, but you can't make a conclusion about your population mean based on your sample. I mean, you can't just look at the smallest of the sample means and say that that will have the smallest population mean. We can't use ANOVA to say that. We can only use it to say that they all have equal means, or that at least one of them will not be equal. Okay, so let me take you back. Hopefully you've had a chance to look at that. And the notes are also in my stat lab. So you should have them already. There I have the condensed version of it. So what I'm doing right now is I am going to enter all this information on the calculator. And that's what you should see right now. So I'm just going to mute my mic so that I can just enter them. And as I'm doing this, you should do it as well. Stat, and then I'm going to select Edit. And I have some data in here, so I'm going to just clear it. Come back down. I always forget to clear this. There's a way of clearing it before you actually get in here. So I'm going to enter my data, L1, L2, L3. All right, so I'll give you some time to do that. And I'm just going to mute my mic. Okay, so they're all entered. So you just have to be really careful that you don't make a mistake while you're entering this. So what I'm going to do is I am going to see if I can get into one of the homework questions from this, because there is a way of, on the homework, of having your data open up in StatCrunch. So you're not actually entering it on your calculator. All right, but as you can see here, I took some time and I had to enter them all in, and hopefully I didn't make a mistake. I don't know if anybody was watching me as I was entering them, but hopefully I didn't make a mistake. I have the final answer so I can check to see if that was the case. All right, and those are the kind of mistakes you can make. I mean, if you don't get the same answer as I do, that's probably because you entered something incorrectly. So on the final, I may have you enter some data in there. I'm trying to keep it short though. But I could also give you the output. I could just give you the output from StatCrunch or from the calculator and ask you to interpret it, to tell me what it means. And then, of course, during the final, that would save some time because you don't have to spend time entering in your data. Okay, so my data's in there. So remember what we did before. I go to Stat. I go over to Tests. The very last one is ANOVA, so instead of going down, 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 down to get to it, I'm just going to go up, and there it is, ANOVA. Okay, this time when I type in the L1, L2, and L3, this should work because now I actually have data in there. So second 1, comma, second 2, comma, second 3. We only have 3. And I'm going to press enter. All right, so in there, do you see a p-value? Type out the p-value that you see. If one or two of you can just type it in, just so that it's there. There you go. Now, some of you rounded to 3 places. Okay, 4 places. Okay, now, if you're getting a different p-value, then you want to make sure you check the data that you entered. So it looks like the majority of you say 0.028. Right, so if you did not get 0.028, now we should round our p-values to 4 places. So 0.02, well, that's what it would be, because that 79 becomes an 80. So 0.028, yes. Okay. So if you didn't get that, then you want to make sure you go back and check your data. And I am checking my previous work here of when I entered it on my own calculator, and that is what I got, 0.028. That's our p-value. So we really just need the p-value to determine what's going to happen to the null hypothesis, right? That's really what we need. Now there's some other measurements here. We have our f-test statistic. I really never gave you a formula for the f-test statistic. I just told you, well, your f distribution kind of looks like the chi-square distribution. What we know about the f distribution is that it's a ratio of 2 variances, but I didn't really say what the variances were. What you have here is SS and MS. Those are used to calculate your test statistic, your f-test statistic. So I want you to try something. What happens when you take the SS, that's called the sum of squares, and your MS, which is the mean of squares? So what happens when you take 162.86666, and that continues, over 81.43333? Well, that didn't give you the F-test statistic probably, right? What did it give you? I'm just curious. I got you. Okay. All right. So that's not your F-test statistic. Okay. So we do not have all the. So what I'm going to do for the second part of this is explain how the F-test statistic comes to be. So I thought the calculator would give us that information, but it gave us the F-test statistic, the 4.09, and there it is, and the p-value. The most important is the p-value. All right. So I'm going to go ahead and see if I can save that. We'll move it over to the whiteboard. So what we're going to use here is the p-value. All right, so remember we typed that out, so that one's already there. So the setup for our null hypothesis, this is our first step. This is how we write it out. All right, so this is our first step. You set it up. So the null hypothesis has this statement of equality. And the alternate says at least one of the means is different from the other. It doesn't tell us which one. Just at least one is different. They're not all the same. All right, so the first thing is you want to write down the first step for hypothesis testing. The next thing is your what we got on the calculator. Okay, what we got on the calculator. So our p-value is right here, and so this is everything the calculator gave us. Okay, it gave us all this information. Now, if you're using some other software, StatCrunch does something similar, Excel does it too. It gives you the p-value. You notice that there's the p-value. It's the same p-value that the calculator gave us. So just based on that information, you should know what to do. It also gives us this one gives us our critical value, and it gives us our test statistic. So this right here is our test statistic. So I'm going to put TS for test statistic. Okay, so I'm just checking something right now. All right, so I thought the calculator had given this to us, but it was not in the right order. It gave us 81. Okay, so right here, those are the two values I was looking for. So if you take 81.4333 and you divide it by 19.8888, what does that give you? So that's what I was trying to get on the calculator, but I don't think I was looking at it correctly. Oh, here it was. It was the MS, and here's the MS. Those are the ones I had to look at. That's where they were on the calculator. So what we're looking at when we do ANOVA, the calculator does it for us, but we take the variance between groups, and we look at the variance between groups and the variance within groups. So here's your between groups, and here's your within groups. So you take the variance between the samples, and you take the variance within the sample. And when you take both of these and divide them, you get your test statistic. All right, so I think that was 81.433 over 19.888. And that gave us our 4.09. So the F-test statistic is just a ratio of two variances. So then the discussion is, what are those variances for? Where do they come from? All right, and so we'll go ahead and talk about that later. For right now, for this example, what you're paying attention to is your p-value. So the p-value, I'm going to call this, it says step 1 here, but I'm going to call this 2. Our first step is setting it up, and that's 0.028. You had already given that to me. All right, so is the p-value, I think our alpha was 0.05, right? So what do? The p-value is 0.028. So we compare that to alpha, right? We compare it to alpha. So is it greater than alpha or less than alpha? And then we have to decide what happens to the null hypothesis. So if it's less than alpha, that's when we are going to reject the null hypothesis, right? All right, so if we reject the null hypothesis, then we go back to our null hypothesis. We're rejecting it, right? So I am going to cross it out. We just rejected the null hypothesis. So then what we can say is that there's enough evidence in our sample to say that at least one of the means is different from the others. So when you compare chest deceleration measurements among the small, the medium, and the large cars, they do not all have the same mean. That's all I can say, that they do not all have the same mean. At least one of the means is different from the others. And that's the only conclusion we can make about our population. Based on the sample, we can say that all the means are not the same. At least one of them is different. Exactly which one is different, that we cannot say. All right, so I just left mine in 2 steps. So the first step was just to set up your null and your alternate hypothesis. The second step is to get your p-value, and then you're just comparing it to alpha. Okay, so in this case, there is sufficient evidence to warrant rejection of the claim. The claim, in this case, the claim is in the null hypothesis. Okay, so that was our claim for equality. So the claim was that populations have equal means. That was the claim. So our claim is in the null hypothesis, and we reject the null hypothesis. So then this is the conclusion we have from our list of conclusions that we've been looking at. All right, so the third step is to write down what your conclusion is. Okay, now, you see that the data that you're given, you can see what's happening with the sample means. So in this case, let me go back to it. There it is. You can see what's happening with the sample means. And you can see that the large cars have the smallest chest deceleration. And the small cars have the largest chest deceleration. Now, informally, you can look at those means and kind of determine that, okay, I know probably large cars seem to be safer than smaller cars, but you cannot make that conclusion about the population. You can make an observation about what's happening in your sample, and noticing that the mean chest deceleration in large cars is much smaller than the mean chest deceleration in the small cars. There's more movement in the small cars when there's a crash. There's more movement with the body. All right, so we can't say that, though. We cannot make that statement about the population. You can just make an observation, but you cannot say anything formal about your population. All right, and that's all this says right here. That's all this explanation says. So let me read it. Based on the samples of measurements in your table, we conclude that those values come from populations having means that are not all the same. That's the conclusion we make. That's the only conclusion we can make. And this is on the basis of the ANOVA test. What we can't conclude, we can't conclude that any particular mean is different from the others, but you can informally note that small mean is the smallest for the large cars. And this is under the assumption that small measurements correspond to less trauma, less movement in the body. So large cars seem to be safer. But this is not a formal conclusion that you can make. It's just an observation. All right, so the only conclusion you can make is what I underlined. And that is what ANOVA is doing. It's just comparing whether the means are equal or not. Now, if you want to look at the test statistic, and I didn't really give you a formula for the test statistic. We looked at it in the calculator, and I said it was a ratio between two variances, but I never gave you a formula for it. What we note, though, is that the larger values of test statistics, they are going to give you smaller p-values. So if you have large values of your test statistic, the ANOVA test is right-tailed. That's what we note. Larger values of test statistic result in smaller p-values. So if you have a small p-value, you reject the null hypothesis. And if your test statistic is in that shaded region, you reject the null hypothesis. It's a larger test statistic, so it would be in the shaded region. It's a right-tailed test. And then I go to say that the F-test statistic is a ratio of two estimates. It's called the variation between samples and the variation among samples. All right, so this is what I'm going to do. Here's a formula. And so what I need to do is I need to show you a graphic of that. The variance between samples and the variance within samples. All right, so that's what the second part of this lecture is about, is looking at an explanation of what I mean when I say variance between samples and variance within samples. Okay, so let me go ahead and take you to another screen. All right, so I'm going to stop there. Let me take you to another screen. Okay, so this is my goal here is to just try to explain what variance between samples and variance within sample means. So I'm just trying to explain that ratio. All right, so what you should see on your screen now is you should see 3 groups. You have data that's blue from our first group, you have red data, and you have kind of greenish data. All right, so this is data that was collected. It's not real data, it's just made up data. Does learning method affect students' exam scores? All right, so this is made up data. I'm just trying to explain visually what the variance between samples and the variance within sample means. All right, so consider 3 methods of learning. The standard, which is sitting in the classroom and listening and writing down what is being lectured over. That's the first method. Then we have osmosis, and then shock therapy. Okay, I don't think it's legal to do shock therapy anymore, right? So I mean, this is just made up data. I'm just trying to give you 3 different ways, okay? All right, so we have 15 students. 5 students are randomly selected for each method. We wait 8 weeks, then test the students to get exam scores. All right, so this is just made up. I should have chosen something different, but it's just, just for entertainment purposes here. So standard method, osmosis. I hope I could learn by osmosis, and then shock therapy. Okay. So this is my data. So the shock therapy, look at the exam scores. Those are the blue data values. For osmosis, those are the red data values. And for standard method, those are the green data values. All right, so you could see that we have 3 different groups. And so what I would be interested in is, are the means the same or are they different? You could probably make a guess just based on what your data looks like, because you're comparing the data. You could probably make a guess as far as whether the means are the same or they're different. What would your guess be? Are you going to get the same mean for all of them, or do they all have different means? So visually you see that, right? If you calculate the mean, they're going to be different, right? Okay, so what I'm going to do is I'm going to go through the process. So here's just a visual, and I'm going to go through the process and go ahead and try to explain what I just showed you in the other slide, the variance between sample and the variance within samples. Okay, so you could tell here that the variability is different for all of them, right? Some of them are closer together than others. All right, so we see that. So here you're comparing it, and it's just about the same. 50 is the largest on here. Okay, so what happens when variability within is large? Then the data values are further apart, right? Okay, so consider this. Consider that we are going to find the mean of all the data values regardless of whether they're in the first, second, or third group. We will find the mean of all the data values regardless of which group they're in. That is called your grand mean. Let me remind you that I did not condense these slides. They are available on my stat lab, but I did not condense these because this is just, the reason I'm even going over that is just to explain where that F-test statistic, what it does. Right, that was my whole purpose here, is just to explain what the F-test statistic is doing. Okay, so let me consider the grand mean. That's the mean of all your data values regardless of which group they're in. Okay, we're going to call that the grand mean. All right, so the grand mean, I think it was on this one, 61. All right, so the grand mean is where we're going to come back to. Consider also for a moment that we can calculate the mean for all of our different groups. So the triangles that you see here, that's the mean for the shock group. The red triangle, that's the mean for the osmosis group. And then the green one, the green triangle, that's the mean for the standard group. So if you look at the groups separately, you can calculate the mean for each group. So we're going to consider the distance of each data value from its own mean and the difference from each data value to the grand mean. And that's the idea here with the samples, the variance between and the variance within. So we're going to calculate the distance from each data value to its own mean and the distance of each data value to the grand mean. That's the idea. Okay, so I'm going to come back to this. So I'm just going to, let's see what the best way is here. I don't want to get you dizzy. I just want to find the best slide here. And I'm almost done on this one. I just want to show you the graphic. All right, here it is. All right, so I'm back on that screen with sort of the same image I was showing you. Okay, so what we're going to start measuring is we're going to start measuring, you remember about variance, and we had a formula for variance. Okay, that was back in the earlier chapters, chapter 3. The average square distance of data to the mean, that's what we called our variance. Now, the formula for variance, as you can see, it's right here. In ANOVA, the sum of squares is called the SST, sum of squared total. And that's obtained from our variance formula. If you multiply both sides by n-1, you get that. So those two are the same. Okay, so the measurement in ANOVA is called the sum of squared total, the SST, the sum of squared totals. That comes from our variance formula. And again, the variance is the average square distance of the data to the mean. So how far away are your data values to the mean? So for ANOVA, we're looking at how far the test statistic, the F-test statistic, is a ratio between how far they are from their own mean and how far away they are from the grand mean. So you're looking at two variances. All right, so here the grand mean was 61. And so when you find, you see all the arrows, when you find the distance from each data value to the grand mean, that is your sum of squares total. All right, and that is obtained by doing the following. So the sum of squares total is the distance that each data value is away from the grand mean. And that's going to be obtained by taking the sum of squares between plus the sum of squares within. Okay, so the sum of squares total gets partitioned. And this is how we get the sum of squared totals. You're going to calculate the distance that each data value is from what's within its own mean. So you're going to calculate the distance that each data value is from its own mean, and then you're going to calculate the difference that each group mean is away from the grand mean. Okay, this one is very important. Let me go ahead and take a snapshot of it. All right, so you see these right here? So how far are each of the group means away from the grand mean? All right, so here it is. So I'm back to the other part. So this is our summary here. So your sum of square total is our sum of square between plus our sum of square within. So the f-test statistic is a ratio of these two, the sum of square between and the sum of square within. So the f-test statistic is a ratio of the sum of squares between, which is the distance that each mean is away from the grand mean, and the sum of square within is the distance, the average distance that each data value is away from its own mean. So in analysis of variance, in order to determine whether the means are equal or not, you have to understand variance. You have to analyze the variance. You have to measure the distance that each data value is away from its mean and the distance that each mean is away from the grand mean. All right, so I just kind of wanted to throw that out there to say that it is, even though we are testing means in order to say something about the population means being all equal or not, you have to understand variance. It comes from understanding variances, the variance between and the variance within. And again, variance, all right, let me pull it up. That was my definition. Here it is. Variance is just the average square distance of the data to the mean. That was back from chapter 3. Okay, all right, so there's a lot that was said there. The most important part of that was that in order to determine whether the population means are all equal or not, is you have to study what's happening with the variance. So you look at the variance between the sample and the variance within the sample. All right, and that's what this is all about. Okay. All right, so the next thing I'm moving on to is when we want to test for equality of 3 or more populations, we have to use ANOVA. We have to use analysis of variance. So we can't start testing 2 populations, maybe the first 2, the next 2, the last 2. We can't do that. You can't test 2 populations at a time. If you're testing more than 3 means to see if they're equal, you have to make sure you're using analysis of variance. You cannot test 2 means at a time. All right, and this is more explanation on the variances between samples and the variances within samples. And so that's what I said at the beginning. This could be a very short lecture, or it could be a very long lecture, depending on how detailed I go into all of the definitions. So what I have here, and I can just allow you to look at that, but it actually gives you an idea of what happens with the p-value and you can look here at your sample means. For the first group, for Part A and Part B. How are Part A and Part B different? Well, what was changed was the sample data for the first one. Sample data was different. Okay, so that's what's different. So let's see how it changes our means. So here 5.566, those pretty much have, the means are really close. The means are really close. So when you go through the test, look what happens with the p-value. The p-value is greater than alpha, which means you fail to reject the null hypothesis. So when you fail to reject the null hypothesis, you believe that all the means are the same. That's what you can say about our population. And so you choose something where that's actually really happening in our sample, right? And you go through the process. But look at this one over here. The first sample was changed. So look at 15.5. It's pretty far away from 6. Okay, so now, we're trying to see if the population means are equal. When you go through the test, we get a very, very small p-value, which means you reject the null hypothesis. And so when you reject the null hypothesis, that means that the means are not all different. Okay, and you can kind of see it here in the sample, although we can't just look at our sample. But in this case, you could see that one of the means was different. Okay, so if the p-value is small, you reject the null hypothesis. Here it's less than alpha. When it's less than alpha, less than or equal to alpha, you reject the null hypothesis. And the null hypothesis says that the means are all the same. And that's what we're rejecting here, that the means are all the same. All right, so here you have your definitions. There's the variance between samples and the variance within sample. So where did this 0.0833 come from? That, what we do here, that's the variance between samples. So what we're doing is we're taking all of the sample means. We're taking all of the sample means and we're calculating a standard deviation for all of our sample means. So when we calculate a standard deviation, or in this case a variance, that's squared, when we calculate the variance of all these means, that's the average distance that these are from the grand mean that I showed you. So you're going to find the variance of the sample means. And when you find the variance of your sample means, that measures that average square distance of these three values to the grand mean that we talked about earlier. Then of course you multiply that by n, and that's your variance between samples. Now the variance within samples, you're taking all of the variances from each of the different groups and you're averaging them out. So here you have 3, you have 2, and you have 2. Add them together, there's 3 of them, and that measures the variance within samples. So the F-test statistic is the ratio of these two. Okay, so that's as far as I'm going to go with that. There's a lot more that can be said, but I'm going to stop there. I do want to give you a problem to work on. So let me go ahead and pull that up. Okay, that's weird. I had it up here a minute ago and it just disappeared. So we can go ahead and take a 10-minute break. I'm sorry, a 5-minute break. And then that way it'll give me time to go find it again. I had it up here and I think I accidentally just closed it off. So let's take a 5-minute break and then I'll come back. It's about 1:40, so about 1:45. All right? So I'm going to mute this, and when you come back, I should have it up. Okay, so what you see here are, I put a few problems on there. That's the first one we'll start with. And so remember at the beginning of today's lecture, I had mentioned there's several ways that I can give you a problem with doing ANOVA. This is one of the ways where I don't actually give you the data, but I just give you the results. So if I just give you the results, what's the most important thing you have to look at? How are you going to determine what's happening? To remember that. Right, the p-value. The p-value is the most important thing. Okay, so let me go ahead and circle that. All right, so you're looking at the p-value. That's going to give you the information you need. All right, so then let me go ahead and what you do have to do is you have to set up the null hypothesis so that you know what it is we're talking about. Okay, so that's what I'm going to do. I'm going to set up the null hypothesis. So this is how I could ask the question on the final, because as far as time is concerned, you're not actually having to type in data. So I could give you an output, and you need to know how to read the output. You're searching for the p-value. That's really what you need. Okay, so the null hypothesis, we have different diets here. Weight loss from different diets. So study of the Atkins, Zone, Weight Watchers, and Ornish weight loss program involved 160 subjects. Each program was followed by 40 subjects. The subjects were weighed before starting the weight loss program and again 1 year after being on the program. The ANOVA results from Excel are given here. Now it says use a 0.05 significance level to test the claim. So you know it's a hypothesis testing question. Test the claim that the mean weight loss is the same for the diets. The mean weight loss is the same for the diets. So you have 4 different diets here. So 1, 2, 3, and 4. You have 4 different diets. So we're comparing the means. We're comparing the mean for the 4 different diets. Because we have at least 3 means, you have to use ANOVA. So the first mean is equal to the second, is equal to the third, is equal to the fourth. So the claim is that the mean weight is the same for all of the diets. So that means that the alternate hypothesis says that at least one of the means is different from the other. All right, so that is your first step. Your second step is the p-value. And then the third step is just telling me what happened. All right, so is the p-value, we're comparing it to alpha. So if you're comparing it to alpha, alpha is 0.05. So 0.7877 is actually greater than alpha, right? So what does that tell you? Okay, so if we fail to reject, the null, then you have to believe the null, right? And the null says that they're all the same. So given that the mean amount of weight loss after 1 year are, okay, now this right here is your sample means. I didn't even use that. I just looked at the p-value. So do the diets appear to be effective? So what do you think about that? Do the diets appear to be effective? The weight loss is the same for all diets, according to this. So from the sample, the conclusion we can make about our population is that the mean weight loss is the same for all these diets. So is one better than the other? Not according to this, no. Okay, and that's it. That's all you have. So you set it up. That's the null and the alternate. You look for the p-value, and then you write your conclusions. So I put the mean weight loss is the same for all diets. All right, so that's one way in which I could ask you the question, where I give you the output, whether it's the calculator output or an Excel output or a StatCrunch output. It doesn't matter. You need to be able to identify the p-value. You have to be able to identify the p-value. So in this case, the proper conclusion, and this is from looking at your conclusions, is that there is not sufficient evidence to warrant rejection of the claim that the mean weight loss is the same for the diets. All right, so that's a lot for me to write, but I guess I could type it out. But remember that that is the conclusion. All right, so this is another way I can ask you the question. You actually have data. That's just like the example we did. This is head injury. The other one was chest deceleration. This is head injury. So listed below are head injury data from crash test dummies used in the same car as we had a chapter problem in the book about this. So these measurements are in HIC, which denotes the standard head injury criteria. Test the claim, or at least it says test. Test the null hypothesis that the different car categories have the same mean. Okay, so again, we're testing that the means are the same. And you have 1, 2, 3 groups. So you have 3 means. So again, this requires that you use ANOVA. All right, so I want you to work on this. You're not going to do it right now, but I just am making this available on the lecture notes so you can have time to read over it. And I'm just trying to put this on there. I just found it and then I lost it. Wow, I'm having some trouble today. Okay, so here they are. Open. All right, so let me show you where to find that. And that's giving it some time to load up. All right, so let me go ahead and look at the next one. So all these will have, I'm just showing you where they're all at. So you're going to have that first problem, that second problem. Okay, now here's another question, and it's coming from chapter 11. So do you think this is an ANOVA question? Are you going to have to do ANOVA here? What do you think? All right, so what does it say here? It says, use a 0.01 significance level to test the claim that successes are independent of the methods used. Yeah, this is one of those matrix questions, right? So you're testing independence. So did we test independence in section 11.2 or 11.3? Do you remember? Yeah, so this definitely is not ANOVA. So for ANOVA, you're testing to see if the means are all the same when you have 3 or more means. So 11.3, that's what this says right here, 11.3. Okay, so you're testing for independence. You're testing to see if one variable is independent of the other variable. And this one, remember, is the chi-squared test. So when you're testing for independence, that's the chi-squared test on your calculator. Okay, and then I have another one. How about this one? Is it an ANOVA question? Yeah, it's definitely not ANOVA, right? Okay, do you think it's an 11.2 or an 11.3 question? So we're testing the claim that the frequencies are all the same or the probabilities are all the same. In this case, it says outcomes. All right, but the outcomes are equally likely. So 11.2, correct? So for this one, you're going to probably remember for 11.2 we had categories. So we had frequencies and we had categories. At a local casino, a die was tested to see if it was a fair die. It was rolled 200 times. And here are the observed frequencies for the outcomes. So a die could either be a 1, a 2, a 3, a 4, a 5, or a 6. Those are your categories. So we have 6 categories. And so the frequency, that means how many times did we roll a 1? We rolled it 30 times. A 2 was rolled 31 times, and so on. All right, so those are your frequencies. That's what actually happened. That's your observation. So do you remember what it was on the calculator? Those 11.2 questions, what command did we use on the calculator? Yeah, so it had something there about a goodness of fit test. It was a chi-squared in the first part, chi-squared goodness of fit test. That's what 11.2, that's what we used in 11.2. Okay, so you have 3 types of questions in Chapter 11. You have a question like this one where it's asking you if the frequencies are equal, or if the outcomes are equally likely, or if maybe the proportions are equal, or if the probabilities are equal. And you only have one row for your frequency. The other one is your category. That's one type, a question. The other one is where you have at least 2 rows and 2 columns. Those are your contingency tables. And on your calculator, that was your chi-square test. So here you're testing for independence. There, I'm trying to underline it, and it's doing some strange things. So let me try a highlighter. All right, so here you're testing for independence. One variable is one variable independent of the other variable. And then the one for today, we're testing to see if we have the same mean. And I know we tested means in Chapter 9, but we only tested 2 means. This one, you're testing 3 or more means. So that's the breakdown of Chapter 11. All right, so I'm going to take you to my Stat Lab. All right, so here we are. If you go to Lecture Notes and you scroll all the way to the bottom, I put it on today's date, but it's the Chapter 11 practice. So if you click on Practice 1, that's what you see. All right, and so you can print that out and work on it. And there's 2 of them there, and there's actually more questions I have for you. But notice that I say, show all your steps. That means you have to show me the steps for your hypothesis test. So you have to, step 1, null and the alternate. Step 2, test statistics. Step 3, p-value. Or maybe you did the traditional method of hypothesis testing. It's up to you. So you have to show me all your steps in your hypothesis test. You can't just give me the p-value and tell me what's going on. You have to make sure you organize it. Give me all the steps. All right, so that's practice 1, and then I have practice 2. And practice 2 was the other set of problems. All right, I think we did this one, but this was the other set. So that's your chapter. That's what chapter 11 comes down to. All right, so what I wanted to do next, and so that's what you're going to do for today's lecture. I actually didn't give you an actual assignment today to get credit for the lecture. You're just going to go ahead and work on these 2. And under homework, I've already assigned homework number 15. I'm done with 11, so you can finish this, although it's not due until, well, you still have some time for this. Yeah. So notice that when you hover on the questions, it tells you where it's coming from. So here's an 11-4 question. So when you click on your homework, it opens up. All right, so here's a question from 11-4, I believe. And so here you have 4 different groups. All right, but you see how the data values, they're not that bad. So you would enter L1, L2, L3, L4, and here you're comparing 4 means. So that's not too bad. I'm just wondering if I gave you one where there's a lot of data in there. Here you just have the output. So p-value is what you're focusing on. You just have the output, so you look for the p-value, see what it is. All right, so I'm just looking at the data to see if, all right, I found one. Okay, so this is number 6. I don't know if it'll be the same number 6 on your homework because it does alternate. Everybody's homework is different. The same questions, but it's slightly different. Okay, so for this one, there's a little icon here. You could hopefully see it. It says click to copy table. So if I'm clicking on it, it says open in StatCrunch. So the alternative of having to type this out in your calculator is that you can open it up on StatCrunch. And there it is. There's your data. You don't have to type it in. If you go to Stat, there's ANOVA right there. We only considered one way ANOVA. So you say one way of ANOVA. Now, what columns are you looking at? You're looking at all of them. So you type them all, you click on them all, and what I had to do, when you click on each individually, it doesn't select them all, so I have to click on one and then hold the Shift key to click on the rest. All right, so all we want is a basic ANOVA, so nothing else really needs to be, I don't need to do anything really. So what are you looking at from that output? And there it is. All right, so if you're getting anything from this class, the one thing hopefully you will never forget is the p-value. What does the p-value mean? If your p-value is less than alpha, then you reject the null hypothesis, whatever the null hypothesis happens to be. Okay, and the null hypothesis always includes equality. The null hypothesis is always a statement on equality. So if the p-value is less than alpha, you reject the statement about equality. Alpha, when it's not given to you, 0.05 is the default. All right, so it's the p-value. Yes, the p-value, that's what you look to. So whatever the output is, you have to go and look at the p-value. So that's just an alternative. I don't know if you have more questions where there's a lot of data, but your alternative is to go to StatCrunch. And then you can just do ANOVA on StatCrunch. Okay, and I think that's all I have for today. So here's what I'm going to close all this down. So what I want you to do for next week. So here's your announcements. So on your announcement page, you already have everything I'm asking for here. Okay, well there's one thing that's on the announcements page, and that's your StatCrunch Lab number 2. So there is something on there, so you want to make sure that you start working on that. It is due on the day of the final, so make sure you start on that soon. Okay, so if you scroll all the way down, your sample midterms were down here. So what you're looking at is final exam review. Now one change that I made this semester, is what the final is going to cover. Okay, so I want to talk about that. Okay, so there is a question that says where is the classroom for the final? I still have not given you the classroom. I know there is a classroom for it. I still do not have that information, but this is where it will be. Once I have where the room is, it's going to be posted at the very top under announcements. Okay, so it will be posted at the very top. It'll tell you exactly what room to go to, and it'll tell you the date of your final and what room to go to. Right, so it'll be at the very top. So that's under announcements. Okay, so the final exam. The final exam will cover the second part of the semester. Okay, so you've already had a midterm over chapters 1 through 6. And that score was recorded, and that's done. Your final exam is going to cover 7 through 11. And so what are your reviews for 7 through 11? Well, they're all right here. Now, one of them, you have all the keys there. Yep, all the keys are there. All right? So your job or your homework is to go through these reviews. I labeled them as Review 1, Review 2, Review 3. And so you're going to work on these. And next week you're going to bring questions to me. And we're going to go over the ones you didn't understand. But you have to be able to try them out first, because if you don't force yourself to try these out, then you're not forcing yourself to recall that information, and you're going to have a lot of trouble on the final. So I would don't do all of the reviews. Use one of them to practice, Review 1. All right, and that's the one I could probably answer questions on next week. Although I'm good with all of them. If you have whatever your questions are, I'll answer. But I would suggest that you do one of the reviews and go through it, review, do the problems as much as you can. You may need to get help, and that's fine. But I want you to leave one of these reviews so that you're doing it on your own. You need to, at some point, test yourself to see how much of this you can do. So put yourself in a situation where you have to do this in 2 hours. And you are only allowed to use that one page of paper, one sheet of paper. Now, what I'm going to do is I am going to give you a pre-made page where I'm going to put all the formulas for 7, 8, 9, 10, and 11. And what I'll do is I'll make it available here. It's kind of already here if you go to Study Guide. but I'll condense it and I'll put it into one page. So here's the review of all the chapters. And so chapter 9 and 10, it's all on here. So what I'm going to do, since I have this already in the format, I'm going to condense it and put it all into one page. But I'm going to have to delete a lot of stuff on here, a lot of extra stuff. I'm just going to put the most important information. And then I'll leave that as a doc format so that you can edit it. So either you just print it out and write by hand, you're going to write out whatever formulas I left out, or you can type them out if you want to, since it will be a document, a Word document. All right, so that will be coming to you. For right now, you want to make sure you begin your review for the final. Begin your review. And I'm only going to be available next week. After that, I'm unsure as to the times I'm going to be in my office. Because everything changes on final exam week. So next week, week 16, is the last week I'm available, according to what I say on the syllabus. All right, so that's your homework. Go over the review. And of course, you do have your last homework from chapter 11. So make sure that you go and you finish the homeworks that are already there, and then you probably have quizzes on here as well. So make sure you finish those. All right, I'm printing out the participants list. Okay, so I will talk to you next week. And next week there's no new material. It's just you showing up and asking me questions about the review that you've been doing. I am going to just keep checking your homework and your quizzes, because there's some other stuff that might pop up on there. Okay? All right. So I'll talk to you next week. Have a great day.